I'm David Rochero. Today is Tuesday, August 24th. It's 10:34. I welcome you from La Burlache, Córdoba, Argentina. Thank you very much for joining this presentation, Organic Matter in Soil Under No-Till Systems, what we learned, which were the progress made, and what we expect for the future. This presentation is part of the soil symposium in the 25th Aapresid Congress. Siempre Vivo, Siempre Verde, always alive, always green. We are going to emphasize the importance of soils in ecosystems, the management of soil to keep it healthy, and to keep it the same as the motto of our Congress, always alive, always, forever green. In this presentation we are going to listen to now, we'll have a Q&A session, so you can start sending your questions in the right side of the screen. You can prepare your questions through the presentation. In the top menu of the main website, there is a section entitled Participants or Speakers, and you will be able to receive information from the speakers. Also, remember to visit Aapresid space in the commercial hall, where you will find live interviews with experts and content for participants. And to follow us in the social media, use the hashtag Congreso Aapresid. Joao Carlos Moraes will start with his presentation. Joao is a master in agronomy at the Rio de Janeiro Federal University. He has a PhD in soil science from the São Paulo University and Ohio University 2001. He has a postgraduate degree in the carbon in the Ohio State University. Since 2007, he's the president of the Brazilian Commission of No-Till. He's also a research professor in Ponta dos in Brazil University. He has usually being present in several Aapresid Congress. So, Joe, take the floor, please. Good morning, everybody. It's a great pleasure to be here to share with you all this knowledge. In the first place, I would like to thank Aapresid and the organizer committee for this opportunity, and especially to my friend and almost brother Cesar Bechoso, who got me in the phone to make this final invitation. I've been with him since the first edition of this Congress in 1992 in Villa Giardino until to date, which is the first edition, the first virtual edition. Thank you for this. Today we are going to talk about organic matter under no-till. What is it that we learned, which was the progress made, and what we expect for the future? This is the summary of 25 continuous years research. Many things happened. We got to know many innovations and many new things. I will make a summary and I will highlight the most important items. In order to understand this context, we need to have an inspiration. Inspiration for me in this case was Mother Nature. Why? Whatever happens in Mother Nature is closely related to all we did. So we have our first questions. What are the lessons learned from Mother Nature on soils? What is it that we learned? Number one, in any forest, the soil is permanently covered. This is very important. Number two, in forest, we have a huge biodiversity. This biodiversity with time promotes an original structure of the soil that provides continuous flows of carbon, water, air, and nutrients that interact where physiological, chemical, and physical aspects interact. The soil without anthropogenic disturbance, the stratification of organic matter and nutrients occurs in the deep profile of the soil. So it goes down, and this becomes a natural process that is ruled by the continuous flow of carbon, which enriches the surface soil, the topsoil, and it goes down in time. And this creates the flow I have just talked about. What we did? What is it that we did when we started to produce food? Deforestation, felling down trees where we used the wood, we burned them, and so we generated the emission of all the carbon contained in this vegetation. Then we leveled the floor. We started with intensive tilling, and we continued creating emissions or generating emissions. And this is the way we started with agriculture. And which were the impacts of this on soil organic matter? We first need to understand that the rupture of microaggregate and the exposure of cementing agents have suffered the attack from microorganisms. When we broke the soil, these agents are attacked by microorganisms. The most important components, the humus, the fungus, hypha, this microstructure get dispersed, and that begins with physical restrictions. There will be an increase of soil density. Water won't be able to be filtrated, and there we start with what we call cementation. So this is the way we started to produce food. The consequence is the total collapse, the total collapsing of all these aspects: water, air, nutrients, and carbon certification is also lost. What's the scope or the magnitude of carbon loss? This is a case study in 3 regions with contrasting climate. It is based on 3 sites. The first, it's a tropical altitude climate with average temperature of 18.5 degrees centigrade. A transition area, Londrina and Paraná, 71% clay, 21 degrees centigrade, and the third region is 48% clay, low altitude, and another temperature averages. First, we have to ask what is the original carbon stock in vegetation and in the soil? Okay, this is the carbon stock both in the native vegetation, in the air part and in the roots and in the soil. The green bars show the carbon stock in vegetation, and the brown bars show the stock in of organic matter in the soil. In Grossa, the site in Ponta Grossa have 312 tons of carbon, Londrina 236, and Luca Rio Verde 225. With agriculture, we change this number. How come that this happened? Because we established a balance or a budget for each region. In woody soils, it have 54.3 tons. With the felling of trees and deforestation, we lost most of it because due to vegetation conversion and due to a continuous tillage through 29 years, this the loss is minus 8.4. But we need to understand why this happened. For Londrinas, these are natural fertile soils, are soils with a natural saturation base above 50% pH without any restriction. Here we had 95.5% of tons of carbon we lost with tree felling, this amount of carbon, and with continuous tilling we have a loss of 47.3%. This means 143 tons of lost carbon, and in the tropical area we had 95.6 of carbon stocks. We lost it, and with 10 years of continued tillage, we lost 27 tons. And so this makes a total of 122.7 tons. How did these losses happen in Pontegrosso, Londrina, and Luca Rio Verde? Here we add soil to vegetation, and here I'm adding one more indicator, which is the stubble equivalent. That is straw plus roots. 190, 609, and 528 tons stubble equivalent in each of these evaluated sites. What happened in the subtropical altitude areas with clay soils? The main losses were in the surface layer at 0.20. And then an increase in deeper area. What happened? Because compounds that have movement in the profile, they experience a migration because temperatures are different and rainfall is heavier, is higher. In Londrinas, we have a high natural fertility soil. We lost 47 tons. There are also losses in deeper area. And this makes this very clear in the tropical area. This tropical area where 54% was lost in the surface layers and 45% in the subsurface layer. Why did this happen? The first answer is related to rainfall distribution. Blue and green are the rainfall areas, and red are the drought areas or the dry periods. So if we don't have coverage, a green bridge or a stubble bridge, as we call it, what happens in this period? We have the water that has been stored during rainfall, and it promotes decomposition. And due to a capillarity movement, it promotes a dislocation of organic compounds that can be volatilized. And this occurs during the dry periods. And the absence of coverage or of cover will speed up this loss process. So in places where by nature we don't have the soil which is permanently covered, we will have problems. We have talked about the total carbon. Now we are going to talk about the fractions, because the ones that change the most are the fractions. So we divide the organic matter fractions in three groups: the particulate carbon, with a size of 0.053 to 2 millimeters. These are compounds that are very labile, and they are associated with macro aggregations. Carbon associated to mineral are smaller, 0.053 millimeters. They are more stable, and they are associated to the clay fraction. And the carbon associated to minerals, but this is a recalcitrant, is very small and very stable, and they make up the clay humus complexes. If we look at the total carbon in the soil and the distribution in the fractions, we see that we get away from a more subtropical area and we go to the tropical areas. We will see a balance in the amounts of this fraction, and this is promoted or stimulated by the biological activity that speed up the changes, the transformation of organic compounds. So we have a 130 tons, we have 44 tons of particulate carbon. Let's try to understand this change. 19%, 19 tons, which means 7.4% of total carbon, 10.734. These are the losses. And how did losses occur in the profile? The trend is quite similar. Ponta Grossa, which is a cooler area, our first impression is that we need to understand this to establish management strategies. These are more labile compounds that have a greater impact in the first stages of stubbles into carbon, into soil carbon. This is important information. This also happened in the Londrinas, in the transition area, but in the tropical area, it is still very strong. Not only the losses at the surface layer, but also losses in the subsurface layer. And this confirms the theory that has been presented a short time ago about the processes of volatility and carbon emission or carbon losses. Let's associate this to the minerals. We have a higher percentage for them. Losses are also different, so much so that in Ponta Grossa, which is the altitude area, an increase was observed. But where did this increase occur? If we had total carbon migration to the more deeper areas, this happened with the carbon associated to minerals. So a loss of 2.5, but an increase in the others.
The
trend in the warmer area and in the tropical area changed. In the transition area, we see a very fertile soil, loss of surface, and in the tropical area, we see similar losses in almost all layers. This shows that these processes go through very intense changes. And we see a unique situation here. There was an increased loss in the colder area as compared to the warmer area. In the colder area, there was a marked loss in the 0-20 layer. The same trend could be seen in the transition area and the tropical area, with a distribution mostly due to different types of clay with an increased capacity to bind and produce harder, more complex carbon. Well, having said this, we'll see what the consequences were. There was an impact on soil carbon. So here we see the soil with this carbon distribution from the surface all the way to 6 centimeters deep, and we see that the stratification is quite marked. We see the gradient from the surface to the depth, and the calculation was made dividing carbon concentration on the surface layers and the deeper layers. We have 0.5, 38.3 divided by 7.1, 5.4. In intensive tillage, everything was changed. Conventional tillage shows that there is a marked reduction in carbon content. In summary, in a subtropical region with clay soil, good rainfall distribution with no extended dry period, the more marked carbon losses happen in the 0-20 centimeters deep layer. And there is migration of carbon to the deeper layers. To what extent is the mean average temperature higher and associated to rainfall scheme with an extended dry period and with no soil cover during this period, the greater sea losses in the deeper layer. The better soil fertility and associated to a high mean temperature and good rainfall, the greater the losses of carbon in the superficial and deeper layers. This is a very important aspect because it will guide management strategies for us to be able to increase our productivity. Now, what happens with chemical, physical, and biological attributes of soil when there is organic matter loss? First item. So the first thing is aggregation, porosity, and infiltration go down. And there is an increase in soil density and penetration resistance. And this affects root development, water storage, air absorption, as well as water and nutrient absorption. So and when this happens, these other things happen. Chemical attributes. There is a reduced cation exchange capacity, reduced nutrient cyclage, and there is an increased redox potential. This affects cation retention, nutrient availability, and finally, the biological attributes. The key thing is the reduction of carbon and nitrogen flows. Consequently, as a result of an increased decomposition or breakdown rate and increased nitrification and mineralization rates. This affects conversion, storage, and mostly the protection of carbon in the soil. And finally, the carbon-nitrogen flow and biologic activity. So, there is a negative, if there is a negative impact on carbon loss, will be deconstructing the whole system. The whole system is associated to carbon. All attributes that regulate the increase or that's the increase of production or support systems that will be more sustainable in time cannot be affected by this, which was the progress made. First lesson. If we turn to no-till, there is no longer topsoil, and now there is a richer layer with crop residues that will change organic matter dynamically. With time, carbon, nutrients, stratification is recovered. This is the big lesson, 1993. And then we learned that if we add quantity, quality, and frequency, we will be able to achieve some changes. Using the carbon-13 technique, we identified C3 and C4 systems. This is soil depth, 0, 2.5, the first small layer. These are the carbon particle size fractions. 100% in the first layer of the thicker fraction is carbon coming from roots and stubble. When we go down, we see a reduction here as well. It's a gradual process. This represents continuity, and up to 10 centimeters we see that the contribution of stubble goes down, but that will depend on the quantity, quality, and frequency of the contribution. This is key because we have different types of soils. With different characteristics. This is a soil with no physical restrictions. This is a different type of soil with physical restrictions. When we monitor, when we quantify carbon in the 040 layer and 40 to 100, for a soil where there is forest with 20 years of no-till, we see that both in the case of little or very clay soil, we see on average 55% of carbon is in the up to 40 centimeters layer, and below that it's 45. And after 20 years of no-till, situation has not changed so much. It went from 55 to 58. And we see the same trend in the lower layers, where the situation is quite similar. The conclusion is we have to develop a strategy to move forward with an agriculture with more carbon and a higher capacity to resist dry seasons. We have to invest in carbon in the subsurface. This is quite clear. And we have to think how we can add carbon, but knowing what the different types of clay are, because the relationship between clay and carbon is a close relationship. This is the 0-10 layer, 10-20, 20-40, 40-70, and 70-100. I would love to point out this here, the increase coefficient, 0.06. It goes down as we go to the deeper layers. Why? First of all, in this layer, we see more biological activity, more air, more water, and the transformations are more intense. The lengths are more stable, and in the deeper layers, 0.02, 3 times less, there is less oxygen, less substrate, and less biologic activity. So what do we have to do so that the roots at this depth will get the carbon they need, because there is a carbon deficit. So we need oxygen. And how can we get that? Through the roots. we need to contribute biologic activity. And how can we do this in layers up to 100 centimeters? We need to use roots that have different and robust components. So the conclusion is, first of all, we need to suppress the oxidation of the surface layer. And how can we do this? This is an important piece of work done in 2012, loss of dry mass associated to loss of soil coverage. This is an experiment with different types of service crops, cover crops, in this case, black oat. We managed, we roll, we do pesticide application, and 13 days later, the first sample, it went down to 94.5%. And with time, during the development of the soybean crop, it kept going down until 19.2% at 160 days. During this period, we see flowering at 65 to 75 days. The demand for water for grains to be filled will be very important, so the soil needs to have at least 50% cover. The more, the better, because in this way we will be able to transform water into biomass, and the soybean crop that was close to 20% of cover, it contributed over 3,500, which is double. So here we close the window and we do not allow the soil to be bare. But in order to achieve this, we need to know the carbon balance. Yesterday, Professor Wall talked about part of this topic, and I'm going to supplement his vision. For us, carbon balance was the second major lesson. Why? When carbon input is lower than carbon output through oxidation, carbon going into the atmosphere, we have a negative balance. And the soil behaves as a source of carbon emission. This is very important. Secondly, when what comes in is more than what comes out, we face the opposite situation. The soil is going to behave as wasteland. So we need to define the projection system strategy based on this. So which was the progress achieved? Third lesson. Understand what a no-till system is about. It's a system based on three main pillars: no tillage, continuous soil cover, and diversity in crop rotation. This is what Mother Nature taught us. We also need to understand how we go through the no-till evolution stages. This is something we did in 2004. We divided the system into four major phases: initial phase up to 5 years, transition phase 6 to 10 years, consolidation up to 20 years, and maintenance phase over 20 years. And what do we achieve in the different phases? Low straw accumulation, low breakdown, reestablishment of biomass, microbial biomass, and fauna with no mobilization of nitrogen, reduced nitrogen demand for grass crops. As time goes by, we see changes, and these changes are going from low accumulation to large accumulation on the surface with increased carbon and increased cation exchange capacity, increased microbial biomass, and reduced nitrogen response. This information is shown on this graph. We see the carbon content going from immobilization being greater than mobilization during the first 5 years. It becomes equal at 10 years. Then we see here some periods which are the same as some period where the relationship is reversed. In this case, immobilization is always going to be smaller than mobilization. This is the maintenance phase. So it is key to understand where we are standing. What system is it? What stage are we in? It is key to know this so as to try and change our strategies. This is fundamental. And this is a question that I have had for 20 years. What is the minimum amount of stubble I need to keep carbon balance and increase soil carbon? Well, there are two situations. In the subtropical area, we have a long-term experiment. This was planted in 1998 and it is still there. And we did our assessments in 2002, 3, 4, and 5. These are planting sequences, winter, summer, grain production, winter, summer, annual carbon, addition, humidified carbon, breakdown rate, carbon loss, stock, sequestration, average. So with conventional tillage, you can see the sequence. Black oat, white oat, wheat, corn, soybean. You can see the balance is negative, but when we included corn in the system, the balance became slightly positive. And this is very important because with this rate, with this breakdown rate, 0.033, the process is intensified. There is continuous breakdown. And you can see what happens with continuous no-till. Permanent cover, more diversity, quality, quantity, and frequency. There is a reduced breakdown rate from 3.3 to 1%. And throughout all the sequences, the balance was positive. But the main support for this system is a corn crop, which is compensating. You can see that here. It is compensating carbon sequestration, or it is compensating humidified carbon. You can see 88, 293, 111 tons. So corn is the one doing the compensation. So the sequestration rate was 0.8. This means, first of all, that soybean after corn produces an additional 500 to 1600 kilo of grain per hectare. This is great. And 3.09 soya 2002, and then corn 357, 388, 3.21, 376, and 456. And these are the compensations produced by the different crops in the system.
What can we say with this? That we have a sequestration rate of 1.62 to when we change from conventional tillage and to achieve a 0.8 increase that resulted in a carbon increase in soil. Why is this important? We are going to work with this table. Management system, carbon budget or balance, a stubble equivalent, conventional tillage, continuous no-till, the two rates, and for balance, for neutrality, we need 16 tons. For conventional tillage, we add a 1045, so the result is minus 5.59. Continuous no-till, we need 6.56, and we contribute 13, and so we end up with 6.52. So if we want to have a more sustainable system, we need to contribute the necessary amount for to achieve the balance. So we need the 10 to 12 tons of stubble per year in order to increase carbon. So in this case, we are going to offset the balance. The tropical area is completely different. This was a trial done in 2015. The X axis represents the neutral balance. When these lines pass through the X axis, this represents the zero balance. This represents 5.3 to 6 tons of carbons in the stubble equivalent, almost 12 to 13.3. If we want to achieve greater sustainability, we need to work in this range where the balance will be positive, and therefore we need to contribute from 17 to 19 tons. So reflecting on what we're doing now, if we are working with these contributions, we are experiencing a successful trend because systems are operating with lower risk, especially regarding climate changes, excess dryness, excess drought, or on the contrary, excess moisture. To summarize and to close this part, in a subtropical region with clay soils, with regular rainfall, with no dry period, we need 8 to 10 tons to keep a zero balance and to accumulate carbon and to walk into a more resilient system, 2 to 12 tons For the tropical region, 12 to 14 tons to achieve zero balance, and 17 to 19 to make progress toward a more sustainable system. The strategy for success in achieving a sustainable productive system needs to intensify sea inversions based on three pillars: quantity, amount, that is tons per hectare; quality, type, grass crops, legumes, or mixture that will contribute carbon and different compounds to promote a carbon increase. And finally, frequency. If we do, how often we do it, once a year, 2 or 3 times a year, and how many crops we intercrop. So what we expect for the future, if we look at what we did and how much we lost, what is the minimum amount that we need? So if we know all that, now we need to establish strategies. The system that we are working with, was it enough? Apparently it was, because Ponta Rosa recovered 17.1 more carbon. This is a rate of 0.55 tons per hectare. In this case, 100% of the lost carbon from the soil was recovered. But this holds a very important message. We don't only need to be concerned with the recover of carbon that was lost due to anthropogenic anthropogenic use of the soil. As the professor says, we need to think at different levels. We need to consider the forest, our natural capital. How long will it take to fix this? We have 77 years left to recover corn. Is that a good thing, or carbon? Is that a good thing or not? In the transition area, we lost much more carbon. We recovered 19. The rate was 0.83. It's enough to cover 40% of soil carbon, only 16% of vegetation carbon. In this case, we will need 150 years. These responses is showing us or how far or how closer are we to recover. If we invest or we continue using an intensified agriculture. And in the tropical area, we had a recovery that was equivalent to 6.4 years. I'm talking about soil carbon recuperation. The sequestration rate is 1.66 tons because we have grass crops and we are mixing all the time. We need almost 70 years. This is the challenge we are facing today. What are the strategies to first increase the sequestration rate? How can we increase capture or sequestration efficiency? And how can we reduce the recovery time? So the challenge is to be more efficient in capturing carbon in the deeper areas. We always talk about the layers from in the 0.41 layer, but we need to go further down. In this study, during 30 months, we uh, uh, he prepared an incubation period without oxidations, and we were able to sequester 72 tons of carbon in 30 months. Ponta Grosso from 0 to 20, 20 to 40, and 40 to 100. That is the layer, the depth. And in these other columns, we see how much more, the more carbon we contribute, the less efficient we are. Why? Why? Why there's not a positive correlation? The first thing we need to think about is how to do the mixtures so that at the same time we achieve biological activity, protection of carbon in the clay soils, and stability of this carbon. What is happening is that uh, we are having a significant loss because we have a very high CN ratio. And look in a deeper zones, there is a change, but it's not a very sharp change. We have 13% of efficiency in our accumulation because in deeper layers have scarce nutrients, especially phosphorus, calcium, and magnesium, and in some cases presence of aluminum. And in the tropical area, 24 to 13% efficiency in carbon conversion. So we are going to contribute more, but we are not talking about contributions. That's why we need to discuss about mixes. The presence of grass crops and legumes. So this balance will be very important because we will, on the one hand, achieve a very robust carbon, and the other one would have carbon with some other components that will help stabilize the process. How can we achieve this? Look at the different profiles, the different depth levels. We need to look for or recover carbon not only in this layer but also in other ones with service crops that have robust roots, aggressive roots, and deep going roots that are tolerant to nutrient scarcity and tolerance to acidity. When a millet, a forage sorghum, brachiaria, we change things with this. Why? Because we are going to contribute a lot of carbon in the 50 centimeters layer, and we will continue contributing carbon in the depth layers as well. So we are going to change the efficiency percentage or the efficiency rate of accumulator because together with the roots we are bringing along a biological activity, exudation, all the process that has to do with this carbon process. How shall we build a new aggregation state and recover soil's functionality or function? We start with the forest. Look at the forest in perfect balance with the macro aggregates, everything together. We change. We convert the system into agriculture, so we cause the collapsing of structures. The magic word is diversification. Why? Because crops as these ones mixed with soybean, millet, corn, brachiaria, there is a huge amount of different kind of crops with different kind of roots that would create a new cementing or cementation. This cementation will happen with different kinds of compounds that come from exudation and breakdown of straw, that is, of the air part and the roots of the plants. Conclusions. I will make a summary of some thoughts because there are many things that I wasn't able to mention, but I think that the key point is that we need to fell a tree to increase or double production. We have the knowledge, the technology, and the strategies to revert, to recover degraded soils or degraded sites with a no-till management. We will be able to recover and achieve another level of agriculture, produce more with less. Yesterday, somebody talked about this, and our conception is to reduce losses, to cover the soil, to recycle more. This means diversity, and increase the efficiency of what we use, fertilizers, irrigation, water, inputs in general. So if we increase efficiency, we will be able to produce more with less. Close windows between the rainfall period and the dry period with green bridges, with service crops, or with straw, with stubble, to avoid losses of carbon and water. Also, root rotation. This is an important practice to create biospores, a new structure, cementation, aggregation, and flows. And finally, intensification of conservation agriculture is based in supplying carbon on 3 pillars: quantity, quality, and frequency in the adding of straw and roots. I would like to close this presentation saying thank you to all those who contributed, the lab team, students who worked all these years, and our teacher, Professor Lal. We have a partnership of more than 20 years.
Bueno, muchas gracias.
Thank you for your comprehensive and great presentation. I'm now going to ask you some of the questions I received. The first question is, do carbon losses depend on temperature, warmer or colder soil, or on texture, percentage of clay? That's a very important questions. It's a synergy. And so far, it has been difficult to isolate both effects. The temperature, the colder, the higher the conservation effect. It goes down, and there is less activity. The cycles the transformation intensity goes down. But in this area, we have higher temperature peaks and lower temperature times. That is always a mixed effect. On the other hand, clays play a key role. For example, I'm going to make 3 comparisons: clay 2:1, clay 1:1, and iron and aluminum oxide. The effects are quite different. Clay 2:1 have natural calcium as a cation bridge. That's natural. And clay 1:1, such as kaolinite, the process goes towards the negative charge. And it's even more so in hydroxide. There's no permanent charge. It's all pH changes. So the bridges are made with iron or aluminum. When we go towards a different type of agriculture, when we change calcium content, we also have the lower activity claim increases activity thanks to calcium. So very soils with lots of clay have a stronger contribution, even which is even in colder or warmer temperatures. Do you understand my answer? Yes. As everything in agriculture, it depends. At school, at university, we learn that it all depends. It's not necessary that when there is an increased temperature, there is increased loss. So thank you very much for your answer. Let's go towards the next question. No-till projection system and area with high crop rotation, legumes and 2 crops a day, and higher temperature. Can you keep an increased grain production and increased carbon content in the soil? Good question. Let's start with 2 points. Number 1, even in
continúa. Entonces,
in temperate areas, the process continues. So when the soil surface is covered, we change some flows, even temperature flows. The temperature change in the surface layer is more stable because there is a buffer. That means that even with colder temperatures, there is still a buffer, and that is important because when we mix legumes with a lower CN ratio and a higher contribution of carbohydrates and nitrogen, nitrogen will become the main component to achieve carbon stabilization. That's an example. If we have, let's say, a fence for cattle, and nitrogen works as a nutrient that is going to stay in the outer part of carbon, but will provide stability. At this time, the legume may help a lot to achieve stabilization with other crops. So, in temperate areas, we need less carbon to meet the demand Well, now we can do carbon reversal to achieve a system with more liquidity. That is a system that is generating carbon even in these temperate areas. The reduction of carbon and nitrogen flow that promotes an increase in organic matter in the soil is associated to the soil biologic matter. That is a question I know you have dealt with this in your presentation, but we might go back to this topic. Well, for the sake of time, I was not able to show my nitrogen data. We have the same information for carbon and for nitrogen, but since nitrogen has an almost 1-to-1 ratio, the ratio varies from 0.89 to 0.9596. That is, when carbon changes, nitrogen changes as well. The carbon-nitrogen flow is key because it's going to stimulate different types of the soil microbiota. For example, nitrogen stimulates bacteria, complex fungi, while carbon has a more general stimulation effect. It acts in all communities, just like nitrogen, because it is important for protein. But at this time, the carbon-nitrogen flow will be very important for macroaggregation. For example, polysaccharides, long-chain polysaccharides that bind to nitrogen give us greater stability for the first macroaggregates. For example, a mix of vetch and black oat, hairy vetch, or cowpea and brachiaria. That's going to be a very good stimulus for this initial stabilization, which is macroaggregation. That's the most important step we have to take in no-till, regardless of the grain system, of the agricultural or cattle breeding system. Macroaggregation is key. Thank you. I'd like to add something to your last comment about hairy vetch together with grass. Well, since you mentioned Cesar Velloso, who's a member of the Pergamino Regional Office, they point out, as a result of rotation intensification, that when adding vetch in rotation, they have been able to achieve increased carbon content, and this is related to what you've just said. There is another question. How do you see the integration of livestock in these no-till systems? Soft grazing of service crops, specifically in our area. We're starting to see this. What do you think about it? That is service crop and adding livestock. Well, I would say there is kind of a ladder. Grain system with crop system adding livestock, crop system, grains, livestock, and forest. These are different complexity levels. When we add livestock, to the production system, we change things. Why? Because we're stimulating the root development, because livestock will eat the aerial part, and that is very important. It cannot go down from a certain height. That is, we do need some biomass on the soil to promote the rebuilding of the new plants for forage to grow. This is key. Another benefit is that depending on the intensity on animal density, we will have the feces, and feces play an important role because it's a type of easily oxidizable carbon that will act almost like a gum. It's carbon that's going to bind to disperse particles, and this will contribute to aggregation. So the animal stepping on a biomass layer that will not go through the development restrictions, that is the ideal thing. It's a wonderful system. For example, 176 is the rate, but today in the same region with livestock, we are working with 2.2 up to 2.7 carbon sequestration rate when we add livestock, and almost 3 with the grain, livestock, and forest system. So it's one step forward in the complexity of the system. That's the real agriculture we have to build for the future. There's one specific question. It is close to where I live in the center of Argentina. Here, our soils are 70 to 90% sand. And one of the participants here is asking the following. He says he lives in my area. He says he lives in an area that produces groundnut. And he asks, is it possible to have a positive carbon balance by adding this crop in rotation? Excellent question. I'm writing an article on carbon balance in sandy soil with 12-13% of clay. Everything changes. First of all, the basic concept. In sandy soil, the aggregation state is almost non-existent. So the development of, or the formation of structures or aggregates with different sizes is associated to time agents. What are time agents? Roots, transient agents. Which are those agents? Exudates. Exudates, different types of exudates, such as polysaccharides, amino acids, many things. And finally, resilient agents, humidification. For this type of soil, we have to intensify crop types that contribute robust roots that are able, that have a good particle reorganization capacity. Frequency has to be increased too. What does this mean? It means to alternate crops. You cannot have a single crop. If you're going to have soybean, when the leaves are getting yellow, you have to start another crop to take advantage of the water residual capacity so as to create biomass. I always say something that is a mantra for me. In soils with water, we create organic matter. This is a very sandy soil with rainfall issues, so we have to use a mix. You have to work using different intensities in doing system fertilization at the initial stage. That is, we have to stimulate the system so that surface crops will be more developed so as to contribute precisely this. Because a serious issue is if we have 3.3% breakdown rate in clay soil in tropical areas, then the breakdown rate in sandy soil, aerated soil, must be 3.5, 4 or more. So this is short, mid, and long term, but it is possible and it can be recovered. Joao, I'd like to clarify something. In this case, this is groundnut that requires tillage. In order to be harvested, tillage is required. So the question was not focused on the specific characteristics of the soil, but on whether that tillage might have an influence on this situation. It might be necessary to carry out some essays to do assessments, but based on what you've said and based on what you've done in Brazil, your presentation was based on soil cover as a fundamental pillar. So that question was associated to that, because in this specific case, this is a crop, just like potato, that requires tillage to be harvested. This is why the question was not so much related to texture, but to the type of tillage. Well, we have an interesting experience here in Brazil with tobacco crop. It's a crop where all leaves are taken off, and it is very susceptible to diseases, especially nematodes. So in general terms, when tobacco is planted, then tillage and soil reversion is performed. We're doing no tillage with tobacco. What is the key to be successful and compensate the tillage effect? Contribute service crops that may add twice or 3 times as much carbon as what the system needs, because this will, as a result of this, after tillage, after groundnut harvest, you will plant a robust root service crop to reorganize the soil so that in this cycle and in the next rotation cycle, you will be able to compensate, because if you do soil mobilization in an area that was not being mobilized, very frequently carbon losses go back to the level before the conservation agriculture system was started. That is, we go back again. Why? Because now, with tillage, the carbon, the labile particulate carbon, will go out. It will be consumed, and it will be a source for the microbiota that will also consume the carbon associated to minerals. Sandy soil has no aggregation. So we see the particle organic matter complex. So the strategy changes everything.
Muchas gracias. Se nos van consumiendo los minutos.
Thank you very much. We are running out of time. Doctor, it's a shame because really it's very interesting, this sharing. We are going to ask last question that refers specifically how can we invade with roots a profile that has been densified because of loss of carbon, and it makes a penetration and recovery for that reason.
Bien, dice, ¿cómo hacemos para invadir con raíces un perfil que tiene problemática de densificación?
Ok.
The first lesson, or the first thing that we have to try to practice, is to choose crops that are not sensitive to these restrictions, and they have the a penetration or drilling capacity. I recommend to work with the pivot roots together with the fasciculated roots. Why? Because fasciculated root will try to penetrate the spaces of the pivoting roots. Another point here, this process will not occur from one season to the other, from 1 year to the other. This is a gradual process. Therefore, the strategy is to use for that kind of area crops that have a high synergy capacity. And if it is possible to supplement with fertilizer and adjust the imbalance, we were able to revert situations when people were trying to use a chisel plow, but we were able to avoid that and were able to recover. I've always been researching on mechanisms, on looking for mechanisms and trying to understand mechanisms and see how things change. And this helps us to develop strategies for different environments. Thank you, Doctor. Thank you very much. Your contributions have been very valuable. We will probably continue in touch, as has been so far with Aapresid, in fact. So thank you very much for your knowledge. We invite participants to continue joining us in this Aapresid Congress, forever, forever alive, forever green. I also want to thank you heartily, all of you. It's a pleasure and it's a sort of obligation because science that is kept and is not shared it's useless, does not help. So I am very glad to share with you these little things I've learned in the past 37 years. Thank you.